Hello and welcome. In this video, we're going to take a look at how we can multiply two matrices. We have a matrix A multiplied by a matrix B. How do we perform that operation? And when is that operation well defined? Because as we saw, we can't always necessarily add two matrices unless they're the same size. Are there any such restrictions when we're multiplying two matrices? Well, let's take a look at that restriction first and then how we compute the entries in the product. So first of all, if we're going to multiply two matrices, we're going to have A be an m by n matrix. Let's call the entries Aij. And B will have to be an n by p matrix, and let's call those entries Bij. That means that when we multiply them together, we'll end up with the product AB as an m by p matrix. Now, it's worthwhile just to make sure that what we're really saying here is that the n's must match. M and P can be whatever dimensions we want for the size of A and B, so long as n is consistently the number of columns of A and the number of rows for B. Once we have the same number of columns and rows multiplied together, then when we perform the multiplication operation, then P, the number of columns of B, will be the number of columns of the result, and M, the number of rows of A, will be the number of rows for the result. Now, how do we compute each of the individual entries in the product? So in other words, how do we compute, let's say, the entry over here as Cij? Well, it's a little bit of an operation. It's not just as easy as multiplying corresponding entries, unfortunately. What we will need to do is take a look at an entire row of A and an entire column of B and perform a multiplication of a row times a column. So how do we do that? Okay, if we wish to calculate the entry in the ith row and jth column, Cij for instance, we'll have to actually compute what's called the scalar product of the ith row of A. So that would be some row of A multiplied by the jth column of B. So that would be some column of B, corresponding to the same row and column of the entry in the new matrix. So, how do we define the scalar product of a row and a column? I've written that row of entries of A as just a single row matrix, or a row vector if you wish to call it a vector, and a single column of the entries of B. And that would be called a column matrix or a column vector. A vector is simply just a single row or a column of a matrix. Now, the scalar product is defined by multiplying corresponding entries as we go across the row and down the column. So, the first thing we do is we multiply ai1 times b1j. And then we go over one more in the row of A, and we'll end up at ai2. Still in the same ith row, but now the second entry. And we'll multiply that by the second entry down in the jth column of B, which would be b2j. And then the third entry multiplied by the third entry until we reach the last entry in that row multiplied by the last entry in that column. And every time we do this, we will add all of the results together to find the total. So the last entry in row I of matrix A will be multiplied by the last row of the jth column of B. And that is how we compute a single entry. Of course, if these are very large matrices, each one of the entries in the new matrix is quite a computation. Well, let's see if we can just do an example or two to understand how we multiply two matrices together. Okay, I've got three matrices, A, B, and C. All of them are different sizes. We have a 2 by 3 matrix, a 2 by 2 square matrix, and a 3 by 2 matrix. Now let's see if we can calculate some products. Let's start with A times B. Now A is a 2 by 3 matrix, and we're multiplying that by a 2 by 2 matrix. And we'll see that the 3 and the 2 here, the number of columns of A does not match the number of rows of B. So this would not be defined. What if we were to try multiplying B times A? Now we can see we have a 2 by 2 matrix, and we're multiplying that by a 2 by 3 matrix. The 2's do match, so we should end up with a result that is now going to be 2 by 3. And that would be the number of rows of B and the number of columns of A as our result. Okay, time to make a little mess here with the highlighter. Let's look at the first row times the first column. And that will give us the first entry. -2 times +2 plus 1 times -1. That should give us -5. Once again, we'll take a look at the first row, multiplied now by the second column. -2 times 3 plus 1 times 5. That'll give us the entry in the first row and second column. And then we'll take a look at the first row multiplied by the third column. That'll give us the entry in the third entry of the first row. -2 times 0 plus 1 times 1. Now we can start looking at the second row of B, and we'll multiply by each of the columns as we go across the columns of A to get the entries in the bottom row of our product. 3 times 2 plus 0 times -1. 3 times 3 plus 0 times 5. 3 times 0 plus 0 times 1. And now we have our result. Let's try one more. Let's take a look at AC. Now A is a 2 by 3 matrix and C is a 3 by 2 matrix. So it should be possible to multiply the two together. Now remember, we used the first row of A times the first column of C. So there should be 3 entries now. 2 times 0 plus 3 times 1 plus 0 times 3. That'll give us the first entry in our result. And we're going to have 2 columns to do this. So we will end up with 2 columns in our result and 2 rows to repeat this, and we'll end up with 2 rows in a result. A 2 by 3 matrix when multiplied by a 3 by 2 matrix is a 2 by 2 matrix. Well, try this out and see if you can come up with the remaining results. Might be worthwhile to pause the video and check and see if you've got the answer. And there we go. Check your answer and see if you got it correct. Now, a little note before we end this video that we do use common shortcuts as we do with exponents in regular values and not just matrices. A squared is really just A multiplied by A. Now that's only going to be defined if A has the same number of rows as columns. So in other words, A would have to be a square matrix. And last but not least, that we do have a very interesting matrix that is a great one to multiply by. It's an n by n matrix where we use 1s across the diagonal and 0s everywhere else. We call this the identity matrix. And let's take a look at why that might be. Let's try multiplying I times C. Now we do have a 3 by 3 matrix multiplied by a 3 by 2 matrix. So it should be defined. Now take a look at the first row multiplied by the first column. 1, 0, 0 times 0, 1, 3. Because of all the zeros in this identity matrix, the only thing we actually have to worry about multiplying is 1 times 0. And that's going to be the first entry in our brand new 3 by 2 matrix. 1 times 0 is 0. Now the first row and the second column, again, the only thing we have to worry about multiplying is the 1 by the -2, which keeps the -2. Want to go down to the next row, 0, 1, 0 means that the only time we actually have to worry about multiplying corresponding entries is for this 1. 0, 1, 0 times 0, 1, 3 is really just as simple as 1 times 1. And if we look at the second row, second column, 0, 1, 0 times -2, 0, 4 is also just going to be 0. You might be already seeing the pattern. When we get to the third row, first column, 0, 0, 1 times 0, 1, 3 is 3. Third row, second column is just 4. And you can see that the result is actually equal to C. And that's why we would call it the identity matrix. We keep the exact same entries whenever we multiply by the identity matrix. What we could have done is we could have taken C and multiplied by a 2 by 2 identity matrix using the same idea that 1s are across the diagonal and 0s everywhere else, and see that when you multiply this out, try it for yourselves. You see that this will also keep all of the same values as C originally had. So this is another identity matrix, CI, where I is now going to be a 2x2 identity matrix. So in general, I is an identity matrix where ones are across the diagonal and we have zeros everywhere else. And this is the identity matrix. Now we'll take a look at more implications about that identity matrix, and it's going to show up a little bit more in the next couple videos. But for right now, see if you can make sense of matrix multiplication. Remember that with matrix multiplication, the first matrix needs to have the number of columns that is the same as the number of rows of the second matrix. That way, when we go across the row of the first matrix, we will have n entries, and we're going to multiply that by the column of the second matrix that must also have n entries. And then we do the scalar product of that row vector times that column vector to get each of the individual entries in the corresponding new matrix. So I hope that helps. We'll see more examples of this in class. Thanks for watching, and I'll see you in the next video.